In the last video, we discussed using the half-life formula to find the amount of a radioactive isotope after a period of time. What I forgot to mention was, what is a radioactive isotope? Well, a radioactive isotope is basically an isotope of an atom, meaning it has the same amount of protons and electrons but a different number of neutrons that is radioactive, or emits electrons. So, besides using the half-life formula, you can also use something called the first-order kinetic rate constant. What does this mean? Well, basically, scientists use a simplified equation to determine the amount of substance in an object after a period of time. Here's the equation. The natural log of the final concentration over the initial concentration is equal to the negative kinetic rate constant times the amount of time that has passed by. We can use this to solve a variety of problems, such as the one above. For example, oh sorry, that's supposed to say sodium. Sodium-131 is a radioactive isotope used in the diagnosis and treatment of thyroid disease. Sodium-131 also has a half-life of 8.1 days, which corresponds to a first-order kinetic rate constant, K equals 0.0856 per day. If a patient consumes a sample of sodium-131 of 10 grams, how long will it take for the amount of sodium-131 to decrease to 0.1 grams? So the first thing we need to know is to find the essential parts of the problem. We want the kinetic rate constant, which is 0.0856 per day. So let's highlight that. What else do we want to know? We also want to know that we started off with an initial concentration of 10 grams, and we ended with 0.1 grams left over of sodium-131. We also want to find out what we're trying to find out is the time it took for the sodium-131 to decay. So let's plug in this to our equation. The natural log of the final amount, or 0.1 grams, over the initial amount, or 10 grams, is equal to the negative kinetic rate constant of 0.0856 per day times the amount of time, which will be in days. Because our first order kinetic rate constant was in days, the time that we find will also be in days. So don't forget the variables and units when you plug these into the equation. So let's multiply each by the natural log to find our answer. First of all, what we need to do is to find the numerical value of both sides. So using our scientific calculator, let's find the natural log of 0.1 divided by 10 grams. That is equal to negative 4.61. Let's multiply the right side of the equation. Negative 1 times 0.0856 times t is basically negative 0.0856 t. Now let's divide this equation by negative 0.0856. We divide both sides by that to get t is equal to 53.79 days, which is basically 54 days. In this problem, we have used the kinetic rate order constant to find the amount of time it takes for a sample of sodium-131 to decay over a period of 54 days. You can also use the half-life equation because they also gave you a half-life of 80.1 days. Let's see how we can set that up. To do this problem an alternate way, we will use the half-life formula, which basically states that the final amount is equal to the initial amount times 1/2 to the power of time over the half-life. Okay, so basically, let's plug in the facets of this problem into the equation. Basically, we know that the initial amount was 10 grams. We also know that the final amount was 0.1 grams. We also know that the half-life is 8.1 days. So let's find the time or amount of days it takes for sodium-131 to decay to the final amount. First, we divide both sides by 10 to get that 0.01 is equal to 0.5 to the power of t divided by 8.1. Next, we take the logarithm of each side of the equation. Basically, we know that the logarithm of the base for 0.5 to 0.01 is equal to t divided by 8.1. Let's multiply both sides by 8.1 to get that t is equal to 53.9 days, which is approximately 54 days. Therefore, we can find the answer to this problem by using the kinetic rate constant equation or the half-life equation.